Welcome, everyone, and thank you for joining today. Imagine you're planning a vacation and you find a great Airbnb listing, but it's not quite right. Maybe it's a bit too expensive or not available on your dates. What you really want is to see a few similar options that are available and still match your taste. That's exactly the problem we're tackling today. How can we build a system that recommends similar listings on Airbnb? Listings that feel like great alternatives to the one a user is currently viewing? This isn't just about content similarity, like having the same number of bedrooms or being in the same neighborhood. It's about capturing what users actually mean when they explore listings, their evolving interests, browsing behavior, and preferences, even when we don't know much about them personally. Over the next few minutes, we'll walk through how to frame this as a machine learning problem, the data and modeling strategies behind it, and how Airbnb serves these recommendations in real time. Let's dive in. The problem is to recommend similar listings to a given listing. Here are some good questions to ask in the requirement clarification phase. What's the business objective? What's the definition of similarity? How many listings are there? How do we construct the training data? Let's now look at how we can frame the problem of recommending similar listings as a session-based recommendation task. ML objective. Our goal is to predict which listings a user is most likely to click on, given the listing they're currently viewing, and potentially their recent activity in the session. So the input is the listing the user is currently viewing, possibly with a short history of their previous views, and the output is a ranked list of similar listings sorted by their predicted click probability. Why session-based? This problem is well suited to session-based recommendation for a few reasons. User interest evolves quickly when browsing travel options. For example, a user might start by looking at budget-friendly rooms, then shift toward tree houses or beachfront homes. We can't always rely on long-term user profiles, especially for new or logged-out users, so we model their intent based on their current session. Modeling approach. We treat this as a sequence prediction task. Given a sequence of listings the user has interacted with, we predict the next most likely one. To do this, we learn item embeddings using co-occurrence patterns. Listings frequently viewed or booked together by users are embedded close to each other in vector space. This allows the system to recommend listings that are behaviorally similar, not just similar in content. How it works. Represent each listing as an embedding vector. Use the embeddings of recently interacted listings to summarize session intent. Score candidate listings based on similarity to that session representation, e.g., dot product or attention-based scoring. Return a ranked list of listings most aligned with the user's current interest. Benefits. Captures dynamic user intent. Doesn't require a persistent user ID. Great for cold start or anonymous users. Learns from real user behavior, not just structured metadata. By viewing similar listings as a session-based recommendation problem, we can build a system that adapts quickly to changing user preferences and surfaces listings that are contextually relevant in real time. To build an effective similar listing system, the first step is preparing high-quality data. This involves both data engineering and feature engineering, tailored to user behavior on Airbnb. Data engineering. We begin by constructing our foundational datasets. Users. We capture anonymized user IDs along with their browsing and booking behavior. This allows us to link user sessions and understand how they explore listings. Listings. Each listing is represented with structured metadata, such as price, location, property type, and amenities, as well as unstructured content like titles, descriptions, and images. User listing interactions. This includes events such as impressions, what listings were shown, clicks, what users interacted with, bookings, final conversions. These interactions help us understand which listings are viewed together, which in turn helps define similarity in a behavioral sense. Feature engineering. A key modeling unit here is the search session. A search session is a chronological sequence of user interactions during one visit to the platform. It typically includes multiple listing views, clicks, and possibly ends with a booking. We can think of it as a mini story of a user's intent, where they started, what listings they considered similar, and ultimately what they chose to book. From these sessions, we extract sequential patterns, e.g., listings frequently clicked before a booking, co-click and co-booking relationships, helping us learn similarity through user behavior rather than just metadata, time-based features, such as how quickly users move between listings. The goal is to model listing similarity as perceived by users, not just by static attributes, but by real interactions. Capturing and engineering features from search sessions gives us a powerful behavioral signal to train models that surface relevant alternatives. The goal is to recommend listings similar to the one a user is currently viewing. Since users often browse multiple listings in a session, we can use these sessions to infer implicit similarity. Instead of relying on listing metadata or user profiles alone, we capture similarity directly from co-browsing behavior. Model architecture. We use a shallow neural network, more specifically an embedding-based model, to learn dense vector representations for each listing. Each listing is mapped to an embedding vector of fixed dimension, say 64 or 128. There are no deep hidden layers. Instead, training focuses on adjusting these embeddings directly to reflect co-viewing similarity. Training data, search sessions. We leverage user search sessions, sequences of listings a user clicked, viewed, or booked in a short time window. Example: listing A, listing B, listing C, booking, listing D. From this, we generate anchor, context, training pairs using a sliding window approach. For every listing, anchor, in a session, listings within a small window, e.g. +2, are positives. Listings outside the window, sampled randomly, are negatives. Sliding window mechanism. The window slides over each session. At each position, the listing at the center is the anchor. Listings inside the window are semantically related. We want their embeddings to be closer to the anchor. Listings not in the session are assumed unrelated, and their embeddings should be pushed away. This is conceptually similar to how Word2Vec learns word embeddings using word co-occurrences in a sentence. Loss function. We use a contrastive loss, commonly negative sampling loss, e.g., noise contrastive estimation or skipgram with negative sampling, or info NCE loss. This encourages high dot product or cosine similarity between anchor and positive embeddings. Low similarity with negative samples. Daily retraining. We retrain this model daily using the most recent search session data, helps capture seasonal trends, pricing dynamics, or user behavior shifts, ensures we can incorporate new listings quickly by learning their embeddings as they appear in search sessions. Training is fast due to the shallow architecture and simple loss function. This method offers a behavior-driven, low latency, and constantly updated mechanism to compute similarity between listings, enabling real-time, relevant recommendations right from the listing page. To assess how effective our similar listing system is, we rely on both offline and online metrics. These metrics help us understand whether the system is surfacing listings that users actually care about, especially those they go on to book. Offline evaluation goal. Estimate model performance using historical user data, particularly search sessions where we know what listing was ultimately booked. Average rank of eventually booked listing. For each user session, we look at the rank of the listing that the user eventually booked within the model's recommended list. Lower average rank means the model is doing a better job surfacing the right listings near the top. This metric is interpretable, session-based, and aligned with booking behavior, which is our ultimate goal. Online evaluation goal. Measure how the system performs in real-world usage, via A/B testing. CTR, click-through rate, measures how often users click on listings in the recommended similar listings module. A higher CTR indicates that users find the recommendations engaging. Session book rate, the percentage of sessions that result in a booking of any listing after interacting with the similar listings module. This is a direct measure of downstream impact, not just engagement, but actual conversion. Together, these metrics give us a clear picture of user engagement, booking intent, and overall recommendation quality. Serving similar listings in production involves three core components: training pipeline, indexing pipeline, prediction. Pipeline, each part plays a critical role in ensuring relevant, fast, and up-to-date recommendations. 1. Training pipeline. This pipeline is responsible for learning the embeddings of listings. We use shallow neural networks trained on user search sessions to capture co-occurrence patterns. Embeddings are updated regularly, e.g., daily, to account for new listings, shifts in user interests, seasonal trends. 2. Indexing pipeline. Once embeddings are learned, the indexing pipeline pre-computes embeddings for all active listings. These embeddings are stored in an index table optimized for fast lookups. Tools like FAS, SCAN, or in-house approximate nearest neighbor (ANN) libraries can be used for this purpose. This pipeline is typically run in batch mode, e.g., nightly, after training completes. 3. Prediction pipeline. This pipeline powers the real-time experience when a user views a listing. Embedding fetcher service retrieves the pre-computed embedding for the listing currently being viewed. Embeddings are often cached in memory or served from a fast key-value store. Nearest neighbor service performs a similarity search in the embedding index, efficiently returns the top N most similar listings. Re-ranking service applies business rules and additional machine learning layers to refine the candidate list, may incorporate session context, personalization signals, or diversity constraints. Together, these pipelines support a high-throughput, low-latency, and adaptive recommendation system. By decoupling training, indexing, and prediction, we ensure both performance and flexibility at scale.